Okay, so in this video, Introduction to Random Variables Part 3, I want to show you the advantage of going to probability spaces where the outcomes are real numbers. So recall from previous videos that a random variable is this function taking an abstract probability space with outcomes whatever you like and mapping it onto a probability space that is in some sense the same structure as far as probability is concerned, but has outcomes in the real numbers. Okay, and the advantage is basically that on the real numbers there is algebra and there is calculus. The main thing there that we want is the algebra structure. So in this video I'm going to show you an example of how we can now we're in the real numbers, we can ask questions based on the algebra basically. So let's take two probability spaces which are in the real numbers. So let's take two binomial. They're both going to be distributed binomially. So we'll have 0, 1, 2, all the way up to n, and we'll have another one which is over here, which is going to be 0, 1, 2, or all the way up to an m, up to some m. Okay, and just close that a bit further, because the sun's gleaming on the paper. Okay, I'm going to use the big blue pen then, just to make it more visible. Okay, so I'm going to redraw out these probability spaces just with the big blue pen, so it's more visible. 0, 1, 2 to n, 0, 1, 2, all the way up to m. Okay, so we have these two probability spaces and they're both distributed binomially. Now, something I haven't mentioned in previous videos is that you will often see it written like this: x is distributed binomially np. Now, x, they will say, is the random variable. Now, really, a random variable is the function between our abstract probability space and this one. So let's say we've got our abstract probability space over here, then x is the random variable x is the function mapping our abstract probability space over here onto this one. And really what you should interpret from this is it's saying that this distribution is distributed the same way as this. The probability space on here has exactly the same structure as the binomial distribution on this standard probability space where the outcomes are real numbers. So that's what really that means. It's saying that x is this random variable. Well, that's what's odd about the axiomatic formulation of probability. The random variable x, really the motivation for where that came from is that it's denoting this random probability space over here, the arbitrary probability space that we don't know what it is, but it can be represented by this standard one which has outcomes in the real numbers, and we're saying that, you know, it's the same as this one over here. It's distributed in the same way as this one, so its probability space structure is the same. But x in the axiomatic formulation became the function that links the two together. So I don't know whether this would be better read. X is the random variable which shows that this probability, which maps this probability space, this abstract probability space, onto the binomial distribution, which is distributed np. So the binomial distribution is obviously the probability measure on this standard probability space n, and it's distributed with probability p. So that means that if we draw its PMF, so recall from the previous video, the PMF is this map which maps onto each of these numbers 0 to n the probability of the event that you get that single outcome. So put each of these outcomes in a set by itself, call that an event, and then we can attach a probability to that, and the PMF is going to map onto each of these. It's going to map each of these onto its probability given that, and that function encodes all the information we need. So the PMF for the binomial distribution, so the probability of getting the singleton set containing an element I is equal to the sum. Sorry, not the sum. It's equal to if you want to get if we consider what abstract distribution could be mapped onto here, then the abstract distribution could be if you toss toss a coin n times, how many heads do you get? Then the possible outcomes are you get 0 heads, 1 head, 2 head, 3 head, all the way up to n heads. And you might think, well, those are numbers surely, but you should think of these as these abstract structures with an algebra defined on them. Think of them just as symbols rather than as counting things. We're bijecting the counting thing onto there. And yes, they do have this. Yes, you're using the same symbols, but you're using them really in a different context. We're putting it onto here so that we can do algebra on this. And the real numbers with that algebraic structure, yes, the algebra plays very nicely with the numbers used to count. But the fact that we use the same symbols to do both of those things is in a way a bit misleading, because they are separate structures we are using there. It just happens that they play very nicely, so we often use the same we do use the same symbols to mean counting and to mean let's do some algebra. Okay, so we're mapping that probability space onto here, so we can think of this as what's the probability of getting I heads, and that is going to be where the probability of getting a head is p. So it's going to be, you have to get p, you have to get I heads, so it's p to the power of I. Then you have to get n minus I not heads, and the probability of not getting a head is 1 minus p. And then you have to look at how many rearrangements are there of that, and that is n choose I. So either you can think of that, it's better to think of it in the intuitive sense of that's where this distribution came from, that's the motivation for why this distribution exists. But you could just think of this as an abstract structure. You could just think of it as we've made these symbols 0 to 1 up to n, we've picked these symbols rather out of the real numbers, 0 up to n, and now I'm going to make a PMF, and the PMF is going to be, I will map I onto this. So I'll map it onto p to the I, 1 minus p to the n minus I times n choose I. And let's just prove that that satisfies what we need it to satisfy for it to be a PMF. So firstly, note that p is an element of 0 to 1. And all we need to prove, basically, is that if you think about this, you've got 0, 1, 2, all the way up to n, so all the way up to n here, and we're plotting this value out. So for 0, you'll go put p in, you'll get to the power of 0, you'll get 1 here, to the power of n, you'll get 1 minus p to the n, and then you'll get n choose 0, which is 1, so you'll get here, you'll get 1 minus p to the power of n, and you can do that for each one of them, and basically we know how to get the probability of any other event from the probabilities of the singletons, because any other event is just made up of a disjoint union of some of these, so we just add them together. So that will, if we define the probabilities on the rest of the events just to be given by that process, then it will necessarily obey the countable additivity property. So we just need to check that the probability that this will ascribe to the whole space, so the set containing 0, 1, all the way up to n, is equal to 1, which is just the sum of all of these, the PMF of each one of these. So if we just sum up from I is equal to 0 to n, pi 1 minus p to the n minus I, n choose I, then we would like this to be equal to 1 if it's going to be a valid probability distribution. Okay, so the way that we can think about this is if we think about it as if we use the binomial theorem. So for instance, the binomial theorem says that if you have a plus b to the power of n, that this is equal to I is equal to 0 to n of n choose I, a to the I, b to the n minus I. So that looks very similar to here, where a is, we could let a be equal to p and b equal 1 minus p. So put both of these into here and you will get 1 to the power of n, because p plus 1 minus p is just 1. So that is indeed equal to 1. So this sum is equal to 1. So it is a valid PMF, and basically, so that's just the assertion that the binomial distribution is a valid PMF. So we've got this other distribution up here, which we could say y is distributed binomially MP. So in this one you've got smaller numbers, and it will have it will have a probability distribution on it as well, which we could describe via its PMF. So its PMF is going to map any old value, let's say j, onto it will ascribe it p to the power of j 1 minus p to the m minus j to the times m choose j. Okay, so those are the two PMFs, and now this is the reason it's so powerful to have them in the real numbers. We can make a new probability space, basically. We can say, let's make a new probability space which is x plus y. And the way we're going to define that is we're going to define it by, if you think about it, we have all of these outcomes in the x probability space. So if we just call this probability space for the while, we'll denote this by x and this one by y. So if you take all the outcomes in the x probability space, that's 0, 1, 2, 3, all the way up to n, and basically you're going to add them to every possible version that you could have in the y probability space. You've got 0, 1, all the way down to n in the y probability space. Add them all together and you'll get each possible outcome in x plus y. So 0 plus 0, you'll get 0, 1, 2, 3, all the way up to n. Here you'll get 1, 2, 3, 4, all the way up to n plus 1. Here you'll get m plus 1, etc., m plus 2, m plus 3, all the way up to m plus n. And here we have a new set of outcomes that you could have, and we can ascribe probabilities that you get each of these, and we will ascribe the probability of each individual outcome. So each one of these elements in here will have a probability, and the probability that we will so we're building a PMF again, so we're saying put each of these in a set by itself. So the probability of each one of these in a set by itself, so let's just denote it arbitrarily by a, is going to be equal to, well, it's two things added together. So let's say its two constituents are I and j. It's going to be the probability that you get I times the probability that you get j. So basically we're defining it so that they will be independent. We're just using the independence rule here. What we want to make sure is that this is a probability measure on here. So we want to make sure that if you firstly we'll define the probability of a more complicated event. So if you take bigger sets, i.e. not just unit sets, then we'll define it by just adding up the probability of each of the individual outcomes. And I want to stress that at the moment this free and this free are different outcomes, because this is free from the addition of 2 and 1, whereas this is free from the addition of 3 and 0. So that is a different outcome at the moment. So I'm ascribing a probability to each individual one of these. We've got n times n possible outcomes at the moment. Later what we'll do is gather them all together and say that, you know, all the threes are sitting in an event by themselves. But at the moment we're just calling all of these separate outcomes, and we want to know what is the probability of each of the individual ones. Now I'm saying we're going to ascribe to each of these sets containing a singleton, we're going to give it this probability. So take its two constituents bits, ask what was the probability of each of the constituents, times those together, and you'll get a number between 0 and 1. We're going to define that to be the probability, and we're just going to check that that is a probability measure or a probability distribution, since we're working in the real numbers. The second axiom of countable additivity follows from the fact that we're going to define bigger events, so for instance that event, by just adding together all of the constituent bits. That will assure countable additivity. What we're going to have to just make sure is that if we sum all of this up over all m by m combinations, that it's equal to 1. And that it's equal to 1. So basically that we can substitute in this as probability of getting I times the probability of getting j, where I ranges from, well, it's between 0 and n, and j ranges from 0 to m. Okay, so it's the sum j is equal to 0 to n, the sum I is equal to 0 to n of the probability of getting I times the probability of getting j. Well, as far as this sum is concerned, as far as this first sum is concerned, j is completely independent of this sum, so it can be pulled out into the front here, and then we just sum up the probability of I is equal to 0. Well, we just showed that that was equal to 1. So this whole bit here goes and becomes 1, so you get 1 times the probability of j summed over all j's, and that's going to be equal to 1 as well. So the fact that the prior to probability distributions were probability distributions means that if we define the new probability distribution on this new set of outcomes, that by this formula here we get a probability distribution. Okay, so we now have a probability distribution, we have a PMF if you like, and what we want to know is what is the probability of, we're going to define some events, define new events, and we're going to define events to be let EJ no, I don't want to use EK. Let EK equal the event that you get K, that the number is K, that the number is K. So basically, what I want is the set containing all the elements of this this new sample space. So all A, which is an element of x plus y, such that A is equal to K. So basically, I want you to go through here. So for instance, if we look at 1, there are 2 elements here which are both 1, i.e. 0 plus 1 and 1 plus 0, and I want you to put both of those outcomes into a set and call that the event that you get a 1. And basically what we're now going to do is set up one of these random variables that I showed you in the previous video, because what we're going to say is we're going to say demote each of these events. Say that each of these events is now just an outcome. So basically what we're going to do is we're going to set up a map from our product probability space, which is what this the fancy name for what we've done here, which is we're effectively taking the Cartesian product of these two sample spaces. So this new probability space we defined here, we're splitting it up into events, and now what we're saying is let each of those events, so let this set containing 1s, for instance, I'm going to demote that to just being an outcome now, and we're going to biject it on to the set 0, 1, 2, all the way up to m plus n. And what I want to do is I want to show you that the distribution on here is the same as the distribution on here, where we distribute this binomially. So we distribute this binomially, m plus n, with the probability p. So I want to show you basically that the event that you get a certain number over here is itself distributed binomially, m plus n, by this over here, binomially, m plus np. So I hope I've communicated what we're about to do. What we're saying is we have defined this new probability space up here. We've taken all possible outcomes of adding one of x and one number from x to one number of y, and we got n by m outcomes. Yes, some of them had the same number, but at the moment we're just viewing them as separate outcomes because their constituent pieces were different. So we then ascribed a probability to we made the PM. We found a valid PMF that we could define on here, which would define a probability distribution. So it gives you the probability of all of the singleton sets, and we define that by take the probability of each of the constituent pieces, take their singleton sets and find their probabilities and multiply those together. And we showed that if you sum it all up, if you find the probability of this entire space, that will give you 1. Okay, now what I'm saying is we're going to collect up sets basically in this new probability space, and the sets are going to be given by all the numbers of us, which all of the outcomes which have the same number. So we're going to put all the 2's in a set together, we're going to put all the 3's in a set together, and we're going to go from 0 all the way up to n plus m, which is going to only have one element in this whole probability space that will be in the set, which is the event that you get m plus n. And we're going to basically do this homomorphism thing where we're saying, okay, we're going to say these events are now going to be demoted to outcomes. So we're going to imagine that all of the different outcomes where you could get 3, they're now in a set together, and we're just going to call that an outcome, and we're putting it into this new probability space where we just have the number 0, 1, 2 all the way up to m plus n, and we will map the event that you get a certain number in this probability space up here onto whatever that number is down here. And what I want to show you is that if this is distributed binomially m plus n with the probability p, then that's basically a probability space homomorphism, i.e. this is a random variable linking this one to this one, i.e. that the probability of you getting a certain number here, the probability of each of the events that you get a specific number, the probability of ek, if you like, is distributed binomially m plus np. Okay, so how am I going to do that? So we need some more paper. So if we look at this probability space that we devised again, so we had all the numbers from 0, 1 all the way up to n, and then we had all the numbers from 0, 1 all the way down to m, and we had 0, 1, 2, 2 all the way up to n, we had 1, 2, 3 all the way up to m plus 1, we had m plus 1, m plus 2 all the way up to m plus n. So what we want to know, what we defined that the probability of a singleton, so pick a singleton here, say that, let's do a specific example. So if you have, if you want to know what is the probability of this specific 2, then you take the probability of this constituent happening, and you times it by the probability of the other constituent happening. So there we go, and we define that for all of them. So if you want 3, you do the 1 times 2, etc. So you find the probability of this one in the old probability space and the probability of this one in that probability space. So we know the probabilities of all the singletons. So if I take a set of these singletons, the probability of that set, so the probability of the event that you get k, is equal to the sum of every single way that you can get k times their probabilities. Okay, so how many different ways can you get k? Well, you can either add 0 onto k, or you can add 1 onto k minus 1, or you can add 2 onto k minus 2. So we could let I vary from 0 to k, and then we could take the probability of getting, well, it'll be the probability of getting I in one of them, and then the probability of getting k minus I in the other one. So those are the two ways you can do it. Those are the ways you can do it. So we're summing up the probabilities of every possible singleton such that it satisfies the fact that it is k. So in the case of 2, what this sum means is go down all the possible ways you could get 2. There are 3 here. So you go through this one, you find this one's probability, you add it to this one's probability, and you add it to this one's probability. And that's what this sum says. It's taking every possible combination of these numbers and these numbers that will give you, that will add up to 2 basically. And then we can fit this in. The probability of I, and let's say I was from this one and the k minus I was from this one. Well, the probability of I, this distribution was distributed binomially, so we can replace this with p to the I 1 minus p to the n minus I times n choose I, and we can replace this one by, this one was distributed binomially mp, so we can replace that by p to the k minus I times 1 minus p to the m is it m? Yes, m minus k minus I times m choose k minus I. Okay, so that is the probability of getting a certain event E. So we want to show that this is itself binomially distributed, and then we will have proven what we've got here, which is that when we mapped it onto this binomial distribution down here, the probability of any event was taken to the correct value, because every event was going on to whatever number it corresponds to, and every number was going on to, well, every number was going to go on to m plus n, choose whatever that number is, so we'll say k, times p to the k times 1 minus p to the m plus n minus k. So that's what we're aiming for. That's the probability of k in this probability space, and we were going to biject all the events onto each of these numbers. So we want the probability of event ek to be the same as the probability of number k in this probability space. Okay, so the probability of ek is, okay, so now multiply out. Oh, we've still got the sum there, sorry. We've still got the sum, I is equal to 0 to k. Okay, so multiply this by this, and it cancels. The I here cancels with the negative I here. So we just get p to the k, which we can pull out the front because k isn't part of the sum. Similarly, here, the I, we've got plus I here, and we've got minus I here. So again, it cancels, and we can pull out 1 minus p to the, we'll get an n, we'll get a plus m, and then we'll get a negative k. And remember, k is not part of this sum. You are summing from I is equal to 0 to k. So I is the variable here. And then what you've got is the sum, I is equal to 0 to k. Let me pull the paper up. I is equal to 0 to k, and the bits that are left. So we've got n choose I times m choose k minus I. And then by van der Mon's identity, which I will quickly remind you of the derivation, if you have a set and you of things, and the size of this set is n plus m, you can divide that up into m things and m things. And if you want to ask how many ways are there of picking, let's say k things from the whole set, well, you can say that it's the sum, I is equal to 0 to k, of the number of ways of picking I things from this set times the number of things ways of picking the rest of the things from m. So basically what we're saying is start by picking no things from here and pick all k things from there. How many ways are there of doing that? N choose 0 times m choose k. Then pick one thing from here, pick k minus 1 things from there. How many ways are there of doing that? N choose 1 times m choose k minus 1. And you go on until you pick all k things from here and no things from here. And that's why this is equal to this, and that is van der Mon's identity. So we can replace this here with m plus n choose k. And that is exactly the probability function, the PMF rather, that we wanted for this to have. So that is the probability of event ek happening, and it is exactly the same as the probability of number k happening in this standard probability space. So this indeed was a random variable. The two probability spaces were in a sense, the structure of this probability space here was in this probability space here.